Welcome back to our MOOC on basic steps in magnetic resonance. Today we shall talk about dynamic nuclear polarization, and this is going to be the third and last part of this chapter. Many free radical molecules can in principle be used for dynamic nuclear polarization. Here I give you 4 examples. The trityl free radical molecules with an electron based on the carbon here, the BDPA molecule, the galvanoxyl molecule, and the tempol molecule. It is interesting to see that these molecules have very different ESR spectra because the electron has a different coupling with surrounding nuclear spins, but also because it has different J anisotropy. We can separate these radicals in 2 classes, those with broad ESR line, such as tempol and galvanoxyl, and those with narrow ESR lines, such as BDPA and trityl radicals. These lines are broad or narrow with respect to nuclear Larmor frequencies. For example, the trityl and BDPA radicals are narrow with respect to the proton Larmor frequency, and are on the order of the carbon Larmor frequency. Whereas the tempol and the galvanoxyl radicals have ESR lines that are very broad compared to the carbon frequency and are on the order of the proton Larmor frequency. And because they have different ESR feature, they're going to yield different DNP mechanisms. So let's start with the simple case of a narrow ESR line of very dilute radicals that don't have much dipolar couplings between each other. This is most likely to yield what we call the solid effect. So in order to understand what the solid effect is about, let's consider an electron spin with the narrow ESR line, here the trityl radical, coupled to a proton of a pyruvate molecule. Here you see the 4 energy level of this coupled 2-spin system, and you can already see that there is a large electron polarization across these transitions, whereas the nuclear polarization across these transitions is close to 0. So what we're going to do now is going to shine microwave frequency at a low frequency, and we're going to increase this frequency until something happens. The first thing that's going to happen is that we're going to match what we call the 0 quantum transition here. By matching this 0 quantum transition, we're going to drive transition of population so as to equilibrate the population amongst those 2 energy levels. And this is going to yield a net nuclear polarization across this transition and across this transition here. Looking at the ESR spectrum here and at the microwave frequency here, we're going to sweep through these different values until we reach this 0 quantum transition here. And this is going to yield a net positive proton polarization that will look exactly like the ESR spectrum, but will be shifted by the proton Larmor frequency. Now, if we keep on increasing the frequency, we're going to hit another transition, that is the electron frequency. And by doing so, we're going to drive transition of population amongst those energy levels so as to equilibrate the populations there. So looking again at the ESR spectrum and at our frequency, we're going to sweep right on the ESR resonance and we're going to saturate the electron resonance. And this is not going to yield nuclear polarization in this particular case. Now we can keep on increasing the frequency until we hit another transition that is called the double quantum transition here. And by doing so, we're going to again drive transition of population among those energy levels until we equilibrate the population here. And this is going to yield a net negative polarization on the nuclear spins along these transitions. So again, looking at our spectrum, we keep on increasing the frequency, and we're going to observe a negative lobe with a negative proton polarization. What is interesting to see here is that the distance between this positive and negative DNP enhancement are separated by 2 times the Larmor frequency of the proton. Now, say you have a broad ESR line with respect to the proton frequency, but you still have very dilute electron spins, such as nitroxide radicals. In this particular case, we might observe a differential solid effect. So the effect is very similar to the resolved solid effect that we've seen before. The difference is that instead of yielding a very narrow lobe, we're going to yield a broad lobe at different microwave frequencies. And in the same way we manage to yield a negative lobe, we're going to do the same in a broad manner. The result is that instead of having 2 well-resolved lobes in the positive and negative side, we're going to have a superposition of constructive and destructive DNP effect that will give rise to a differential positive and negative DNP lobe. Again, the difference in frequency between the maxima will be at about 2 times the nuclear Larmor frequency. So now if we look at another nuclear spin, such as carbon-13 instead of proton, the difference between those 2 maxima will shrink down to 2 times the carbon-13 Larmor frequency. So the solid effect is a pure electron nuclear spin process that does not require electron-electron interactions. It is a second-order microwave-driven transition that has, therefore, a fairly low probability and therefore usually requires high amount of power. Now if one has a broad ESR line, such as Temple, and in addition to that has a moderate electron-electron coupling due to a moderate electron concentration, one can observe the cross effect. So starting from 1 single electron and 1 single transition with a high polarization, and then bringing in a game another electron spin, we see that our spin system can be described by 4 energy levels, and that those 2 transitions can be described by the electron frequency of the spin 1, omega electron 1, here, and the electron frequency of the spin 2, omega electron 2, here. Now what happens when you drive microwave precisely at the electron 1 frequency? Well, you're going to tend to saturate this transition and equilibrate the distribution of population among these energy levels here. At the same time, T1 is going to tend to drive back your population to the thermal equilibrium, which is here the highly polarized state. But now, if you consider a coupling with a third spin, for example, the proton spin of this pyruvate molecule, your energy level system will be described now not by 4 but by 8 energy levels. If by chance the nuclear Larmor frequency is about equal to the frequency of the electron 2 minus the electron 1, something interesting might happen. So again, let's shine microwave on the electron spin 1 and let's saturate those transitions. So again, one way to relax now would be by T1 relaxation. But here, since we have a coupling with a third spin, with this nuclear spin, you can see that those energy levels have exactly the same energy. So there is a transition here that we call cross effect that might be allowed. If this happens, population might flow freely from this level to this level of energy, while T1 will of course tend to bring down the populations to the ground polarized state. So if you think carefully, by saturating here, we start to populate those energy levels. The cross effect tend to bring some of the population on this energy level, and the T1 relaxation tend to bring those spins here down to the ground state. And if you do that on a long time scale, longer than T1, longer than the cross effect time, you might end up with all your population distributed on those two energy levels, which would result in a very high nuclear polarization along these transitions. Now we can look at that from another angle. Here you see the population distribution on all the energy levels according to Boltzmann law in a highly polarized state. When we shine microwave at a specific frequency, we tend to equilibrate the distribution of population along this transition here. Now again, we have a nuclear Larmor frequency here that matches the difference in energy between these electron spins here and those electron spins there. And cross effect will tend to redistribute population amongst those energy levels here. And this is going to create a net proton polarization. So again, we can look at our ESR spectrum and our microwave frequency, and we're going to change the microwave frequency until we see here a positive proton polarization. And if we keep on increasing it, we will yield a negative proton polarization here. And what's interesting in this cross effect is that the difference in frequency between the two maxima here, positive and negative, is about the proton Larmor frequency. So again, if we look at C13 instead of proton spins, we'll see that this is going to shrink down to the Larmor frequency of the carbon-13. So cross effect is an electron-electron nuclear spin process. It requires moderate electron-electron interaction, and it involves simply a loud electron spin saturation. So in summary, we have introduced the solid effect that give rise to a well-resolved positive and negative DNP lobes separated by 2 times the Larmor frequency. We have introduced a differential solid effect that give rise to non-resolved positive and negative lobes, also at the nuclear Larmor frequency times 2. And we have introduced the cross effect that requires some electron-electron dipolar interactions and that give rise to a DNP microwave spectra with a positive and negative lobes separated by simply the nuclear Larmor frequency. Thank you for following our MOOC on basic steps in magnetic resonance. This was the third and last part of our chapter dedicated to dynamic nuclear polarization.